It's brown.
Excuse me. Okay, welcome to day 2 of 28 of BME 205, spring 2021. Two administrative notes before we begin today's lecture content. Number one is that I did post the recording of the first lecture of the semester on Blackboard. It's a Dropbox link. The second item is that the solution, there's a version of each slide deck that I post before the lecture, and there's another version that I post after the lecture. And the version that I post after the lecture contains solutions to the practice problems that are included in each of the slide decks. So lecture 1 didn't have a lot of practice problems. Nevertheless, if you want to take a look at those, just download the version that is labeled lecture 1 with solutions. Today we will begin lecture number 2. I will share my screen. I'll try the slideshow for this. Okay. Today we will cover, two of the most fundamental, or three, I guess, of the most fundamental circuit laws. For some of you, maybe most of you, this will be a review from high school physics. But for some of you, you're getting exposed to these laws for the first time. So the three laws that we cover in lecture 2 are Ohm's law, Kirchoff's current law, and Kirchhoff's voltage law. And they are really the foundation for the rest of the course. Everything that we do in subsequent lectures builds on top of these concepts. And in general, the course is very much hierarchical in that you will use all of the concepts that you encounter in the earlier lectures to solve the problems, to solve the more involved problems with the later lectures. So there isn't really a strict division between the lectures. They're very much accumulating as we go through the semester. So last class we defined basic quantities in circuits, namely electric current, voltage, and power. And our job in this course is to be able to solve for those quantities. And in order to do that, we will make use of these foundational laws. We also delve into a couple of kind of shorthand tools for more quickly solving for voltages and currents, namely voltage division and current division. So these are also techniques that we will use extensively in the course, and they are really just applications of Kirchhoff's laws to series and parallel circuits. So for now, we only deal with circuits that have combinations of voltage sources, current sources, and resistors. We do not consider capacitors or inductors or op amps until lecture number 5, I believe. Okay, resistance. It's a intrinsic property of material. So, all materials exhibit some opposition to the flow of electric charge, and that is known as resistance, or the capital R. So everything has resistance, not just wires, not just circuit elements. There's also a distinction between a resistance of a circuit element and the resistivity of a material. And this is the relationship when you're talking about a cylindrical wire that has a cross-sectional area with a cross-sectional area of A and a length of L. And so this cylinder, you can think of it as a wire, is made up of a material that has an intrinsic resistivity called rho. And the longer that wire is, the more the resistance of that wire. So if you double the wire, you're actually doubling the length, doubling the resistance. On the other hand, if you double the cross-sectional area, you're halving the resistance. Right? So I think that should make kind of intuitive sense to you in this, namely, if you make the area of the wire larger, you're giving the electrons more places by which they can traverse that wire. Whereas on the other hand, if you increase the length of that wire, then you're making them do more work. And so the cross-sectional area, increasing the area will reduce the resistance, while increasing the length will increase the resistance. So again, rho here is just an intrinsic property of a material and is completely independent of the geometry, whereas the resistance R is dependent on the geometry. So I don't know if any of you have worked with so-called BNC cables. These often come with a resistance of 50 ohms. So like a standard cable that you will use in a lab for connecting your various electrical devices, for example, oscilloscopes or signal generators, they will come with a resistance of approximately 50 ohms. And the units of rho, the resistivity, is in ohm meters. And you can see that because length is in meters, area is in meters squared. And so for you to get ohms on the left-hand side, you need rho to be in units of ohm meters. Okay, so again, just to kind of drill this concept home, the resistance can change with geometry and also the temperature, for example, but the resistivity is fixed. We always assume the resistance. We work in this class with the concept of resistance of a circuit element, and we will not concern ourselves with the small fluctuations with temperature. And so conductors have very low resistivity, and insulators have very high resistivity. I think that makes sense. So for example, something like Teflon, which is an insulator to both heat and electricity, has a very high rho value, whereas the metals have a very low rho value. And in the middle, you have what are called semiconductors, which I'm sure you've heard of. For example, silicon, which is used to make integrated circuits. So these are elements that are kind of in the middle of this resistivity spectrum. Okay, so we get to our first law, which is Ohm's law. So in high school, if you learned it, you probably just learned it as V is equal to I times R, right? Which is true, but you need to take care now of polarities and current direction arrows. So we have to indicate, when we say V is equal to I times R, we have to indicate the poles, the terminals of the voltage, and the direction of positive charge flow. So in order to apply Ohm's law, and in order to be able to say, the equation is coming, just give me a second, you need to be able to, you have to, I will ask that everyone mute themselves just to make this exercise work over the internet. So in order to apply Ohm's law, we need to specify the polarity of the voltage, namely what is the positive end of the voltage and what is the negative end, and also the direction of the current arrow. And to apply Ohm's law in its canonical form, you will need to ensure that the arrowhead of the current is hitting the positive end of the specified voltage. Okay, so Ohm's law is basically stating that this voltage drop from this point to this point is proportional to the current. In other words, if I double the current, I double the voltage drop. If I quadruple the current, I quadruple the voltage drop. And if I halve the current, I halve the voltage drop. And that constant of proportionality is called the resistance. Okay, so in other words, if the voltage drop across a resistor is directly proportional to the current that is flowing through that resistor. And more specifically, we say that the voltage drop is equal to the current times the resistance of the element. And so if you measure the voltage, and if you measure the current, and you divide voltage by current, you have identified the resistance of that resistor. And so, for example, we say that a resistor has a resistance of 1 ohm if, when putting a voltage of 1 volt across the resistor, we induce a current flow of 1 amp. Right? So 1 ohm is a very small quantity. In the lab, we deal with kiloohms or even mega ohms. And if you look inside circuit boards, you will see similarly high resistance values. And that's mostly because when you use electricity as to process information, you want to do so in a safe manner. And so you want to keep the current as low as possible. Current is the dangerous thing in electrical safety. So as long as you keep the current low, you are ensuring safety. And so there's nothing wrong with computing with milliamps and microamps. You can do the same kind of signal operations on a scale of very small currents. Okay, so now we have the convention that I have already alluded to, and that is called the passive sign convention for Ohm's law. So again, to apply Ohm's law in that canonical form, we need to make sure that this picture holds. In other words, the current arrow has to be hitting the positive end. So what this picture really means is that a positive charge of I is flowing down across the resistor. And as a consequence, a voltage drop of V volts is observed from this point to this point. Okay, so note that I and V numerically can be positive or negative, right? So this is the confusing point for students, is that this picture does not mean that the voltage actually drops from here to here. That is only true if the value of I is actually positive, right? So R is always positive, so that one's easy. V or I can be negative. As long as positive charge is flowing down through this resistor, there's a voltage drop from here to here. In other words, voltage is higher here than it is here. So current passively does not leave the positive end. So that is true as long as I is positive. The value for I is positive. If I becomes negative, if for example you solve Ohm's law and you find out I is negative, what that actually means is that the positive charge is going up in this picture, right? So, and we'll get to a bunch of examples of that. So if that's not 100% clear in your mind at this point, don't fret, because I believe that it will crystallize once it comes down to actually solving circuits and applying Ohm's law. And so we say that there's a voltage drop. Great. We say that there's a voltage drop from here to here if I and V are positive, right? So if I is positive, then V is positive. If I is negative, then V is negative, because R has to be positive. There is no such thing as a negative resistance, physically speaking. So current flows from a higher potential to a lower potential. Now, what happens if for some reason, let's say in our circuit, we have, let's see if my annotation is going to work. So let's say that in our picture, we have, we ignore this now, and we have the current arrow entering the negative end. You can still apply Ohm's law. You just have to write the equation like this, right? Because the reason for that is that, right, you can, I don't know if this is going to help or hurt, but right, this current arrow and this current arrow are saying the same thing, right? It's like me saying, if I take 5 steps forward, that is equivalent to me saying that I just took negative 5 steps backwards. They're identical statements. Okay. And so keeping, see, I just lost my cursor. This is what I'm talking about. Zoom and PowerPoint. All that money invested and they still can't fix it. I had a student last semester show me how to not have to abort the lecture. Give me a second. Let's see. Is this it? Oh, come on. Ugh. All right. So whenever I have to do an annotation, I have to switch out of slideshow mode. Okay, so again, if you can apply Ohm's law with the current arrow going into the negative end of the voltage, you just have to add a negative sign. Okay. So what is a short circuit? You've probably heard of the term colloquially. Hard to say for me. And so a short circuit is just another way of saying that the resistance is 0. Okay, so any element that has a resistance of 0 is called a short circuit. Now, what that really means is that no matter what the current is, the voltage drop is always 0, right? So if you just, and we assume that wires, that conductors are a short circuit. It's not actually true. They do actually have a very small resistance, but we just neglect it in our calculations. So a short circuit is a connection between 2 points that are sitting at the same voltage. In other words, this point and this point are at the same voltage. There's no drop from here to here. Okay, so no matter what the current is, the voltage is 0 because the resistance is 0. So this is, you can think about this in terms of the math. Namely, when R is 0, we say that we have a short circuit, or you can think of it in terms of the physics. Namely, so if this point and this point are sitting at the same voltage, then no matter what the current is, the resistance has to be 0. There has to be no resistance, right? So there's no, the current will just all jump across with no voltage drop. So a short circuit by definition is an element that has a resistance approaching to 0. What about an open circuit? An open circuit is the exact opposite, the other end of the spectrum. So when R is equal to infinity, in other words, when there is so much resistance that no current flows. Remember I said that the current follows the path of least resistance. So if the resistance is infinite, the current will avoid that, right? So if you have so the way that we draw an open circuit is to have 2 terminals that are left open, so they're not connected. So in this picture, no matter what the V is across these 2 points, no current will flow in this branch. Right? Again, and that is because this open circuit has an infinite resistance. So I think that open circuits are conceptually easier for students to kind of understand. It's just a limiting case. Mathematically, it's a limiting case of R going to infinity. And again, that's easy to understand. The current, the electrons are not going to jump across a gap of air to go from here to here. So there will be and no matter what the voltage here is, even if you make the voltage, 1,000,000 volts, you still will not induce the electrons to jump from here to here. So by definition, an open circuit is a circuit element with resistance approaching infinity. All right, any questions at this point? I want to pause just in case any of you are confused. All right.
Yes, I have a question.
Sure.
So if the current goes from positive to negative, the voltage is negative?
Yeah, so if the positive charge, let's look at the previous picture. So if positive charge flows down this resistor, we say that the voltage drop from here to here is positive. In other words, the voltage here is higher or larger than the voltage here. So the drop is positive. The drop from here to here is positive. So for example, this can be 10 volts, this will be 6. Right? So as long as the current is positive, as long as there's a positive charge flowing down here, we will get a lower voltage at this point than at this point. Again, all these concepts do become clearer with repetition. We haven't really done solved any circuits yet. We will though in this class. It's an interesting thing about how the mind learns that simply through you will encounter a concept that you'll read a sentence and you read it and you don't understand it. And something happens over time where if you read that same sentence over and over, not immediately, but over and over the span of days or weeks, that all of a sudden you understand it. And that is a really interesting phenomenon, is that just by being exposed to it multiple times, we develop a comprehension of ideas. And this, by the way, is a perfect segue into um, more advice from me. I have many nuggets for you guys all. Um, Not that I always was able to implement this in my own when I was a student, but it really is. It's not just how much time you spend; it's over what time period you spend it. So when you learn something, it's not just how much time you spend practicing it or being exposed to it. It's how much calendar time has gone by. And if any of you have ever learned an instrument, you may have noticed this. Like, you get better on an instrument in your sleep. Like, you'll learn something, and then you notice that you'll play that same piece another day, even though you haven't practiced since then, and you're better, right? So learning happens not just when you're actually doing it, it also happens just naturally over time. And that is why, and yes, there is a link to the circuits course here. You should start your studying as quickly as possible, because um, really for this course, cramming doesn't work. And there's always students that uh, there's always a few students that don't do well in the midterm, and they're very disappointed, and they come to me and say, what can I do to pull out an A in this course? And I don't have the heart to say this, but it's a very unlikely event. Just it almost never happens. And the reason is that the time that has elapsed has made it impossible for you to assimilate all of the content that is being presented here. So you really actually do need the passage of time to learn content. So this is obviously applicable to all of your studies and all of your learning in life. You learn just by the passage of time. It's not just the time spent reading something or practicing something. And so keep that in mind with this course, because the latter half of the course, unfortunately, is significantly harder. But it's all doable. And in this course, there's always a bunch of people that do very well. And I hope that that is you. Okay. I'll say a few things about resistors. A resistance can be fixed or it can be variable. So I don't think I have to explain what that means. There are resistors whose value can be changed, can be tuned. So the example so this is the kind of resistor that you will use when you get your circuit.
الاختبار بتاعي اللي هو بيخلص اصلا.
Please remember to mute yourself. Thank you. So this is a carbon film resistor. This is also a resistor. These are both fixed, meaning their value is static. You can also have variable resistors, and these are two pictures, two symbols for a variable resistor. So you can actually change the resistance of this element by sliding a knob or something like that. And so the example I always give is, if you've ever bought a lamp at IKEA, you'll often see these types of switches. So lamps that have like a dimmer, so you can change the brightness of the lamp, and all that is just the resistance being varied. So if you increase the resistance, you get less current and you get less brightness out of the lamp. Okay. So these are two pictures of variable resistors, which we do not work with in this course, but they do exist, and you can imagine that they are useful. Another thing that we assume in this course is that resistance is linear. So linearity is one of these concepts that is super misunderstood and very important. A potentiometer is just another word. A pot is another. A pot, not pot, is just another word for variable resistor. So there's nothing to it. These are two symbols for the same thing. I think that they may have a different way of actually tuning that resistance value. But potentiometer is equivalent to variable resistor. We assume that the resistance of our resistors is linear. What that means is that it doesn't change. The ratio of voltage to current is fixed. Now, in reality, there may be elements where that's not true. In other words, where the slope of V over I, so if you draw a tangent line here, the slope of that tangent line will vary slightly depending on how much current you're passing through. So this happens in nature, but we do not consider such cases. We always assume that the ratio of voltage to current is constant. And that constant is called the resistance. Even if you encounter this situation, oftentimes what you will do is you will operate in a range, right? So you will operate, let me just zoom in on this. Even if you encounter this situation, if you restrict yourselves to this portion of the curve, then you basically have a linear resistor. So again, all this is just to say that in nature, there are nonlinear relationships between the voltage and the current. But in this course, we always assume that our resistors are linear. Okay. I need to clear. Conductance. This is a useful concept. So sometimes we want to be able to compute current from voltage quickly, or for whatever reason, we want to work with the opposite of resistance. And the opposite of resistance is called conductance. And so it's the ratio of current to voltage instead of voltage to current. And it is denoted by letter G. So the units of G, you either have the mho, which is ohm spelled backwards, or it's measured in Siemens or capital S, right? So in other words, 1S is a circuit element that passes 1 amp of current when connected to a 1 volt voltage, right? So, nothing really difficult here. 1 over the resistance is called the conductance, which is the ratio of current to voltage. Okay, so again, it's just a reciprocal of resistance. All right, so now we know what the relationship is between voltage and current across a resistor, and now we want to compute the power. And so again, you probably have seen these equations, but so I guess I can derive these very quickly. If you okay. Right? And so we can then say that V is equal to IR, right? Both these things, right? And so you can, if you substitute this equation into here, you get P is equal to IR times I is equal to I squared times R. And that is also equal to V squared over R. And so the important thing is that power varies with the square of both the current and the voltage. So let me. Okay, so in both cases, if your resistance is equal to 1 ohm, then the power is equal to the current squared or the voltage squared. In terms of conductance, we have the power across a resistor. In other words, the power dissipated by a resistor can be written as V squared times G or I squared over G. Right? And these are very straightforward to derive. And so one thing to note here is that power is a nonlinear quantity of current and voltage, right? So you cannot use linearity or superposition. We'll get to that later in the course. Just remember the power is a quadratic in both the current and the voltage. Note that R and G have to be positive. You cannot have a negative resistance or a negative conductance. And therefore, power is always positive across a resistor. The power dissipated by a resistor is always positive. What that means is that the resistor is absorbing the power, right? And obviously, that should make sense because a resistor is a passive circuit element, and passive circuit elements are not capable of injecting energy or supplying energy into the circuit. Okay, some examples. So I'm going to get you guys to try to help me with these. These are very easy. An electric iron draws 2 amps at 120 volts. Find its resistance. Who can tell me the resistance of the iron? Excuse me. We have a chat answer. Yes, 60 ohms. Thank you. V divided by I is equal to 120 divided by 2, which is equal to 60 ohms. The essential component of a toaster, a very reliable device, is an electrical element, a resistor. Yes, those wires inside the toaster, those are resistors that convert electrical energy to heat. So how much current is drawn by a toaster with a resistance of 10 ohms at 110 volts? So your toaster is labeled as having a resistance of 10 ohms and it's operating at 110 volts. So how much current is passing through those toaster wires? 11 amps. Sounds good. I need to have like I wish I could have the chat on the screen so I could see the, maybe I can if I leave this up. Okay, but then I'm gonna lose it when I try. Oh no, it stays on my screen. By the way, do you guys see the chat screen that I have? I'm curious how this works. No, thank you. Collaborate. Where's the collaborate? We only see the slides. Okay, that's good. Because sometimes, anyways, this actually works. Wow, you can put this on YouTube. That's would not be a popular channel, but it's still cool that that feature is there. Okay. Okay. Our next question. In a simple circuit composed of an independent voltage source of 30 volts connected to a 5 kilo ohm resistor, calculate the current drawn from the voltage source, the conductance G, and the power absorbed P. So let's start with the current I here. How do I get I if we have a 30 volt source and a 5K resistor? Yes. So what's 30 divided by 5,000? Yeah, there we go. Bam. 6 milliamps. Very good. What about the conductance? How do I get the conductance?
That would be the reciprocal. So 166. I forgot the units. Is it Siemens?
Just 1/5.
1/5K.
Yeah, so it's going to be 1/5K. So 1/5,000, which is 0.2, 0.0002 or 0.2 millisiemens. And what about the power absorbed P? There's two different ways, or at least two different ways, or three different ways of doing this. I squared over G would work, yes. Yeah, that works. VI works. So which two numbers do I have to multiply? So I have to, right? So I have to square the voltage. So that's 900 divided by 5,000. So it's 180 milliwatts, right? So 900 divided by 5,000. So that's 18/100 or 180 milliwatts. So remember, know your prefixes. I hate to see people lose marks because they couldn't convert from watts to milliwatts. All right, in a simple circuit with an independent current source of 2 milliamps connected to a 10K resistor, calculate the voltage across the resistor, the conductance G, and the power absorbed P. No, I'm not going to penalize you. It's just sometimes you need, sometimes you'll make a mistake in an earlier step or something like that. Sometimes it's, it's the question specifically asks for the answer in a certain number of units. I'm not I try to be a fair grader. I try to be a nice grader. But I'm just saying, which chapter can we use to review this lecture? I believe it's chapter 3 in the textbook, but I'll get that information up. The material goes sequentially through the book. So 2 milliamps and 10K, 10 kilo ohms. What's the voltage, right? So we have to multiply. That sounds right. 20 sounds right because we are multiplying 0.002 by 10,000 ohms. So we get 20 volts. Thank you for those answers. Now, what about the conductance G? How do I get the conductance G in this remember the conductance of this resistor here? Remember, yeah, so it's gonna be less than 10 milli. 10 milli would be 1/100 ohms. Yeah, so yeah, that's 0.1 is right. In other words, 100 micro S. Okay. And what about the power absorbed P? What two numbers should I multiply to get the power absorbed?
You can multiply the voltage by the current.
Yes,
That gives
right.
you 40 milliwatts.
Yeah, so we have the voltage of 20 volts and the current of 2 milliamps. And so when you multiply that out, you get 40 milliwatts, just like you said. Very good. Gonna just close the chat for a second because we get into the next section of the lecture, which is nodes, branches, and loops. So this is not difficult, but it may seem puzzling at first. So just a little bit of topology. So in a circuit, you have nodes, you have branches, and you have loops. And here we will explain what each of those means. So a branch is kind of the fundamental entity of a circuit. So it's basically a connection between two nodes that have something in between them. So for example, a voltage source or a resistor. So for example, in this circuit, we have 1 branch, 2 branch, 3 branch, 4 branch, 5 branch. Right. So this is not a branch because there's nothing in between these two dots. The dots are called nodes, basically. So the nodes of the circuit, the nodes are the points that connect connect the branches, I would say. It's very easy to get the language here mixed up. So we see that we have five elements, 5 branches in the circuit. 1, 2, 3, 4, 5. Now you may be tempted to say that there are 1, 2, 3, 4, 5, 6, 7, 8 nodes. However, there are actually only 3 nodes in this circuit. And so remember what I said last class. If you can trace your finger along any 2 points in a circuit without passing through an element, those points are all sitting at the same voltage. In other words, they are the same node. So all of this here, all of this oval is a single node B. And all of this down at the bottom is a single node C. And then this is node A. So a node is a point of connection between 2 or more branches. Right? So again, for example, you have this branch, and node A connects them. And so the reason that we define these concepts is because circuits can be redrawn. So as long as you keep the same connections between every element, you can redraw your circuit in whatever geometry you want, right? So this is not an example of a redraw that would be useful, but there are many instances in this class where reshaping the circuit is beneficial to solving it. And so notice that node B here is still connecting, for example, the 2 ohm resistor is in between node B and C. So the 2 ohm resistor here is in between node B and node C. Whereas the 10 volt source is between nodes A and C. The 10 volt source is between nodes A and C. So if you don't immediately see the transformation from this picture to this picture, do not worry at this stage. This will become second nature to you as you start to tackle more and more circuits. What is important is that you understand why it is these 2 circuits are equivalent. And the reason that they are equivalent is because every element has the same connections on each side, right? So as long as you make sure that every element is connected to the same node in both pictures, you're fine. And so in this picture, we have 5 branches and 3 nodes. And a loop is the third entity in circuits. So a loop is a closed path starting at a node, passing through some other nodes, and returning to the starting point without passing through any node more than once. Right? So this is a little bit verbose here, but a loop is said to be independent if it contains at least one branch, which is not part of any other independent loops. This is actually, it reads more confusing than it actually is. So independent loops or paths result in independent sets of equations. And so you will, for example, in this picture, I'll just tell you, this is an independent loop, this is an independent loop, and this is an independent loop. Or another way of divvying it up is 1, 2, and 3. And so there's an equation here that relates the number of branches to the number of loops and the number of nodes. Namely, the number of branches has to equal the number of loops plus the number of nodes minus 1. Okay, and so in the previous picture, for example, we can verify that this is true, right? So we have b is equal to 5, n is equal to 3, and L is equal to 3, right? We have 1 loop, 2 loop, and 3 loops. So 3 plus 3 minus 1 is indeed equal to 5. So that's not a proof of the theorem, but it is a confirmation for the circuit that it holds. So these definitions in the box are very important for this course. So 2 elements are in series if they are connected back to back and therefore carry the same current. 2 elements are said to be in parallel if they're connected to the same 2 nodes and have the same voltage across them. Okay, so in other words, a series connection means same current, and a parallel connection means the same voltage. Okay, so in series, elements are in series when they are connected in a chain, back to back. So in other words, there's no other, like if a current enters one element, it has to enter the second. That's the definition of series. Elements are in parallel when they have the same connection on the top and the bottom. So for example, let me just show you some examples in this picture. So in this picture, the 10-volt battery and the 5-ohm resistor are in series, because any current that enters the battery has to go to the 5-ohm resistor. On the other hand, the 2-ohm resistor and the 3-ohm resistor are connected in parallel because they have the same connections at the top and at the bottom. I think we will do some examples now, which I think will be very helpful. I'll put my chat screen back on. Okay. Determine the branches and nodes in the circuit below. Which elements are in series, which elements are in parallel? So first of all, how many branches are in this circuit? Very good. There's 4 branches, right? What about how many nodes are there in this circuit? Please remember to mute yourself. So how many nodes are there in this circuit?
That'd be 3 nodes.
3 nodes. Very good. Yeah, I'm going to touch. Give me just 1 second. Right. So 1 branch, 2 branch, 3 branch, 4 branch. And so the branches are 1, 2, 3, and 4. The branches are like, that's, without the branches, there'd be no circuit. There'd just be wires. And the 3 nodes are 1, 2, and 3. Okay, so notice that we can trace a path along the bottom here without going through any elements. And so the bottom is all the same voltage. And the top right here is also the same voltage. So 1, 2, and 3. So now we have the three branches here. So there are 4 branches. So which branches are connected in series and which branches are connected in parallel?
The 10-volt battery and the 5 ohm resistor are in series.
Very good. And what about in parallel?
The battery and the 5 ohm resistor are in parallel with the 6 ohm resistor, which is in parallel with the 2 amps.
Yeah, that's very good. Yeah. So what you said is what was said here. I'll just say it back because probably a lot of people missed it. So the 2 branches that are strictly in parallel are 3 and 4. But what you also said, which is true, is that, and actually what I'll do is I'll annotate this because I think it'll, of course. We can actually. We can combine this here, right? If you combine the battery and the resistor as a single branch, it's really 2 branches, but if you take them as a collective, then they are in parallel with this branch and this branch, right? And so these are really 2 elements here, but if you lump them together into one, they are all connected to this node at the top and this node at the bottom. So that's supposed to be a plus sign, that's a minus sign. Right, so this, if you take this node as the top and this node as the bottom, then we have 1, 2, and 3. But you don't have, oh, we have a question. Go ahead. Do you want to?
I just wanted to know why the 10-volt battery and the 6 ohm resistor, why they weren't in parallel as well.
Yeah. So the reason is because, so the definition of parallel is that they are guaranteed to have the same voltage. But in this circuit, there will be a voltage drop between here and here, because this 5 ohm resistor is in between them. And so you're not gonna, you cannot guarantee that the same voltage exists across the 6 ohm as exists across the 10 volts. This is obviously going to be 10 volts. The voltage between here and here is guaranteed to be 10. But some of that 10 will dissipate across the 5 ohm and some of it will dissipate across the 6 ohm. So unless there's no current flowing up here, then these 2 will not have the same voltage and therefore they cannot be parallel. Hopefully that makes sense. So they really have to have, the exact same connections. So in other words, if you look at the node for the 10 volt, another way of answering your question is for the 10 volt battery, its connections are between it's connecting nodes 1 and 3. The 6 ohm is connecting 2 and 3. And so because they don't have the same nodes on either side, they're not in parallel. And one last comment about this is that you do not have, it's not either or. You don't have to be series. You can be not in series and not in parallel. For example, the 5 ohm and the 6 ohm are not in series and they're not in parallel. So you do not have to belong to one of the 2 categories. You can belong to neither. All right. Those are some good questions. I'm just gonna take a sip of my water and we will start Kirchhoff's laws. We're doing well for time though, which is good. Okay. So by itself, Ohm's law is not enough to solve for circuits because the current, anytime the current enters a junction, it will split, and you need to know in what proportions it does split. So we have, I just have a question I'm going to read out. Yeah, okay, so we have a question and an answer. So I appreciate, Ahmed, you actually answering the question in the chat. That's great. So Kirchhoff's laws are old, 19th century. And so one dude came up with both of these, and they're both based on conservation laws. So Kirchhoff's current law is just based on the law of conservation of charge, and Kirchhoff's voltage law is based on the law of conservation of energy. So the current law is, we teach it first because it's easier to intuit. It just states that when current enters a split, you can't lose current along the way. So the algebraic sum of current entering a node is 0. So mathematically, the sum of INs, where the INs are all just branches connected to the same node, have to equal to 0. So there's a picture here that will become, that will, I think will be very useful. So current entering a node, you can think of as being positive, and currents leaving a node may be taken as negative. Okay, so I think the picture here will say it all. Okay, so this is the picture. You have a node here in the center, and we have currents I1, I3, and I4 that are entering, and we have currents I2 and I5 that are exiting. So KCL states that I1 plus I3 plus I4 is equal to I2 plus I5. In other words, we can say that, and this is a proof of the law. I'm going to skip through the proof because I don't find it particularly helpful. The only thing that you need to know is that the total current entering a branch has to equal to 0. And so for this picture here, if we assign a positive sign to the currents that are entering the node, so that's I1, I3, and I4, and a negative sign to the two branches that are exiting the node, then we write that I1 minus I2 plus I3 plus I4 minus I5 is equal to 0. And again, this is equivalent to saying that I1 plus I3 plus I4 is equal to I2 plus I5. This is best understood as the current entering a point has to equal the current exiting that point, right? Charge cannot be destroyed. So if you have this much charge entering, then you must have the same amount of charge exiting. Okay, so the sum of the currents entering a node is equal to the sum of the currents leaving the node. So current sources in parallel, for example, right? So we have 3 current sources here. I1, which is oriented up, I2, which is oriented down, and I3, which is oriented up, right? And then we have some IT that's exiting the whole circuit over here to the left. So, and this, I remember from previous years, this has sometimes caused confusion. So I'll try to, right, so consider this point here, right? So you have IT exiting, you have I1 entering, you have I2 exiting, and you have I3 entering. And so you have IT and I2 that are leaving this node, right? So they're on one side of the equation, and you have I1 and I3 that are entering that node, right? So these are the two that are entering the node, and these are the two that are exiting. So in other words, the value for IT is I1 plus I3 minus I2, which is here. And so I think what confuses people is these two here. They, you know, they don't, it's sometimes you don't immediately see that these two currents here, they all have to end up passing through this node. Okay. And the reason we bring this up is that the picture in panel A can be redrawn as the picture in panel B. So these three current sources can be combined into a single source whose value is I1 minus I2 plus I3. Okay, so so in other words, we can collapse these three current sources into a single current source because of KCL. So is there any questions about this this slide here? Okay, I will move on then to the voltage law. So the voltage law is based on the conservation of energy. Right? So it states that the algebraic sum of all voltages around a loop is equal to 0. And so mathematically, this is that the sum of Vm, where m ranges, the index m ranges from 1 to m, is equal to 0. So capital M here is the number of voltages in the loop, or the number of branches in the loop. And Vm is the mth voltage. And this one is also best illustrated with just a basic circuit. So let's take, and again, I'm going to annotate this because, so we're going to start over here, and we're going to go clockwise. And every time where we go from negative to plus, such as here or here, we're going to indicate the voltage with a negative sign. And every time that we go from a plus to a minus, such as here, here, and here, we indicate the voltage with a plus, right? So in other words, the sum of the voltage drops or rises along a loop has to equal to 0. So in other words, for this loop, we have negative V1 plus V2 plus V3 minus V4 plus V5 is equal to 0. And again, the reason, so our convention in this class is whenever you go from a negative to a positive, in other words, whenever you go up a voltage rise, right, this is a voltage rise of V1 volts, you indicate it with a minus sign. And a voltage drop is indicated with a positive sign. And the reason is that there's generally more drops than there are rises in a circuit. And so we like to have the drops with a positive sign. So again, you pick a point, and you can pick at any point you want as long as you start and end at the same point. And you go around and you count up the voltages and you set them equal to 0. That's KVL. And another way of, another way of stating this is that you can just say that V2 plus V3 plus V5 is equal to V1 plus V4, right? And that's what's on the this slide here. That's over here. So another way of stating Kirchhoff's voltage law is to say that the sum of voltage drops equals the sum of voltage rises. It's whatever speaks to you more, you should think of it that way. You will get the same answer whether you implement this or whether you implement this. Okay, so let's talk about batteries in series. So here we have 3 batteries, and they are all connected in series. So V1 and V2 have the same polarity, but V3 has the opposite polarity. So let's say that we apply KVL to this circuit in a clockwise manner, right? So like this. So we start at point B, go up to point A, and then turn around and go back to B, right? So we have negative VAB, and the reason we label this with a negative sign is because it's a voltage rise from here to here. And then we have a voltage drop of V1, another voltage drop of V2, and then a voltage rise of V3. So negative VAB plus V1 plus V2 minus V3 is equal to 0. And what we can do is that we can simplify this voltage here as VAB is equal to V1 plus V2 minus V3. In other words, we can replace these 3 batteries with just a single battery whose value is V1 plus V2 minus V3. So these 2 pictures are equivalent, right? Because at terminals A and B, we will see the identical voltage and current. All right. Let's, I just want to do a few more slides today before wrapping it up. Because this is a lot of new content. And so what I'd like to do now, this is all annotated. So the goal here is to solve for the indicated voltages V1 and V2. Okay, so for parallel, IT is not negative. Let me just make sure I understand this question. So I believe that the question in the chat was pertaining to this. So IT can be positive or negative depending on the values of I1, I2, and I3. So if what the sign of IT tells us that whether the positive charge is going left to right or right to left. So we've drawn the current direction arrow as going from right to left. If I1 minus I2 plus I3 ends up being positive, then the current IT actually goes from right to left. However, if the sum of these three actually ends up being negative, then in reality, the actual physical current is going left to right, despite our drawing the arrow from right to left, right? So you can draw the arrows whichever way you want. It's the numerical answer in combination with the sign that tells you which way the current physically is flowing. Okay. All right, so we are tasked with finding V1 and V2 in this picture. So what laws do we need to apply to solve for V1 and V2? That is one of the laws, yes. And we need one more, right? Because we have two unknowns, so we need two equations. Yep, KVL. So I'll start you guys off for this one. KVL says that -20 plus V1 minus V2 is equal to 0. Hopefully you're all in agreement. That is the application of KVL to the circuit. So right now we have one equation, two unknowns, right? And so the second equation you get by noting that the current, there's only one loop in this circuit, which means that every element has to have the same current, right? And so V1 is equal to I times 2. And V2, so what is going to be the Ohm's law expression for V2? It's actually a question for you guys. So V2 is
20 divided by 2.
what's that? Close.
20
So you have to have
divided
a
by 2?
negative sign here.
Oh.
And the reason is that if you, I have to annotate this. If you draw your current, this is supposed to be a circle. If you draw your current like this, then the positive arrow, then the arrowhead is going down into the negative here. And so, the application of Ohm's law to this resistor is that V2, as is specified, right? Because we were given this polarity. So with this polarity in mind, the value of V2 is equal to I times -3. And now we have the two equations and two unknowns. And so we can simply substitute into the KVL equation. And we arrive at -20 plus 2I plus 3I is equal to 0. In other words, I is equal to 4 amps, which makes V1 equals to 8 volts and V2 is equal to -12 volts. Okay, I'm gonna just make sure if there's any questions about what we did here, please jump in.
Actually, I have a question because I got a different answer.
Sure.
What I ended up doing was setting V1 minus V2 equal to 0. And then I put 2I minus 3I equals 20.
Yeah. So it's very close. So if you had, so 2I plus 3I does equal to 20. So that part is right. The only thing is, you're almost right. It's just that notice the polarity here is that there's a minus here and a plus here instead of plus and minus. So I think you said V1 plus V2 is equal to 20, you said?
It was V1 minus V2 equals 20. So 2I minus 3I.
Yeah, so it should be,
Oh, I think it should be 2I minus -3I. Is that it?
yeah. So Well, it's should, okay, so if you look, are you looking at my PowerPoint right now? Just, if I point to it, do you see what I'm doing?
Yeah.
Yeah, so it is 2i plus 3i is equal to 20, right? This equation here. I think I'm trying to figure out, because I can't see your piece of paper, which makes it harder for me, but it should be v1 minus v2 is equal to 20. But those are both the same. Those, you should get the same answer, actually. If you got v1 minus v2 is equal
Oh,
to
I see.
20.
I think I see what I did wrong here, actually.
Yeah, based on what you said, you should get the same answer, I think. But if not, I'm gonna post this this to the Blackboard after the lecture.
Okay, yeah, I got it. Thank you.
Okay, awesome.
Professor, I have a quick question.
Go ahead.
So when you first do Kirchoff's law, you're already taking into consideration that the V2 is in the other polarity, correct?
Yes.
So you're doing it again in Ohm's law?
Yeah, you keep that polarity, right? Because V2, like the polarity of V2 has to be the same for both equations. Otherwise, otherwise it's like two different variables.
Okay, thank you.
Yeah, so the polarity will be, it's a good question. The polarity has to stay fixed throughout the problem. And so the polarity is given to you. And by the way, you wouldn't normally write the polarity like this, but it was just to illustrate that Ohm's law, you have to take care of, to put the right sign in front of the I times R, depending on how the polarity of the voltage is specified for you by the question. Okay, so I already have an answer for the second circuit here. We have negative 10 plus V1 minus 8 minus V2. That looks right. Let's check that. Yeah, looks right. So that's our first equation. And our second equation is going to be the application of Ohm's law, which is that V1 is equal to 4 times I, and V2 is equal to negative 2 times I. So now we simply plug those back into the KVL equation. We rearrange the terms and I arrive at I is equal to 3 amps. Okay, and so once we have a solution for I, we can plug it in to solve for V1 and V2. Yeah, exactly. So V1 is 12 volts and V2 is minus 6 volts. All right, next circuit. So here we have something a little bit different. We have a dependent voltage source whose value is equal to 2 times V naught, where V naught is defined here. So let's say I want to start off at the bottom left here. Who can help me with the KVL equation for this circuit? So we have minus 12.
Minus 12.
Yeah, keep going.
Plus 4.
Plus 4i.
Plus 4i. Plus V2. 2v2 or 2v0, I'm sorry.
2v0, yeah.
Minus 4 volts.
Minus 4, yeah.
Minus 6i. Yeah, minus
Yeah,
6.
you can write minus 6i, or you can also just say minus V naught.
Okay.
Because minus 12 plus 4i plus 2 V naught minus 4 minus V naught. And now in this equation, you have your two unknowns, which are I and V naught. And then the second equation is the application of Ohm's law to the bottom here, to V naught, which is that V naught is equal to minus 6i, just like you said. And so now we have the two equations, two unknowns. We can substitute one equation into the other. So we get negative 12 plus 4i minus 12i minus 4 plus 6i equals to 0. We rearrange that and solve for I, which becomes minus 8 amps. And so that makes V naught equal to 48 volts. All right. And then we have our fourth circuit on the page here. So who can help me with the KVL equation starting at the bottom? Why are the first voltage terms for each example negative? Because we're starting at the bottom left and we're going up. So we're hitting the negative end of the battery. So it's a voltage rise. Yeah. So same thing here. It's going to be negative 35 and then plus what?
My electrolysis. It'll be negative 35 plus Vx
Yeah.
plus 2Vx minus
Yeah.
V naught.
Yes. Excellent.
Got it.
And
was
then what
confused
about
the first term?
Yeah, so now we need an expression for either Vx or V naught. So what is the what can we say about let's see, what's the easiest route here?
Well, we can simplify the Vx. So it could just be minus 35 plus 3Vx.
mean 10i?
Explain. So Vx is going to be equal to 35 minus 2Vx, right? But that's we haven't really got. So one thing we can do is that the current through this loop is constant and we just call it I. And so Vx has to equal to 10 times I and V naught has to equal negative 5 times I. Right? Because there's a constant, because this is a series circuit, everything is in series. We can just, we can write that Vx is 10i and V naught is negative 5i. And now we can plug that in to the KVL equation, which you correctly stated for us. And we solve that to arrive at a current I of 1 amp, which means that Vx is equal to 10 volts and V naught is equal to negative 5 volts. So notice here that V naught has a value of negative 5, which means that in actuality, there's a voltage drop from here to here of 5 volts, right? Because the numerical value for V naught is a negative. Okay. Let's see. See if I want to do this. Oh, let me just take a look. I think what I'll do is we'll do one of let's just do them because at the end of the year when we're short on time, I'm going to be kicking myself for not using this time. So this is KCL now. So the current law. So I'll do the first one, and then we'll skip the second one, and we'll go straight to the third one. So we're going to apply KCL at node A here. Right. So we have 3 currents here. Which currents are flowing into A and which currents are leaving A?
Current I naught and 3 amps.
So I naught is leaving, 0.5 I naughts is arriving, and 3 amps is arriving. And so we have 0.5 I naught. Oh, actually, so my solution here, let me, all right, so let me just annotate this so I don't confuse anyone. So we have this current that's arriving. So I actually, in this solution here, what you see here, is just KCL applied at node A. So we have point I naught is equal to I naught minus 3, right? Because this is, and hopefully that doesn't confuse too many of you.
I'm sorry. I'm just confused as to why we're setting it equal to 0.5 I naught.
Because of this dependent source. This is a dependent current source. So the current out of here is guaranteed to be 0.5 I naught. Right? This is a current source.
Okay. All right. Thank you.
Right? So there's 0.5 I naught coming in here. And then some of what exit is I naught here. So really, this would have been better written, and I can actually try to correct this. So 0.5 I naught plus 3 is equal to I naught, if that helps. And when you solve for that, yeah, the diamond current is a dependent source whose value is dependent on I naught here. This is a dependent current source. And so the value of this current source depends on what's happening in this branch of the circuit. But as long as you have the arrow here, this means that it's a current source. So 0.5 I naught plus 3 is equal to I naught. Yes, and 3 amps is independent. So we have I naught is equal to 6 amps. And so V naught is equal to 4 times 6 is 24 volts. What I'm going to do, I'm going to skip the second one. I'm going to let you guys do it on your own time at home. And I'm going to move on to the third one here, which is, none of these are hard, trust me. But this one has a few more steps. So we want to apply, let's see if it will let me annotate. I don't even know why I'm going to try this, but I'm going to try. We want to apply KCL at this node. And so the law is going to be I1 is equal to I2 plus I3. There we go. Okay. I1 is equal to I2 plus I3. But now I need equations for I1, I2, and I3. So what laws can I use to obtain equations that have the variables V1, V2, and V3 in them?
KVL.
Yes, excellent. So who can write? Let's do a KVL for this left loop first.
So minus 30 plus V1 plus V2 equals 0.
Excellent. Oh, I did it differently, but what you're saying is completely right. And actually, hold on, let me see. Let me see if I can, what I'll do is I'll copy the slide over and I will erase everything. Maybe not. We can totally do it the way you're actually here. What you said is here. So actually, I don't even need to do that. I can just. So first of all, I'm just applying the only thing that that we skipped is the application of Ohm's law, which we could have done after. But basically, we know that I1 here is the current that is flowing across the 8 ohm resistor, right? And so we know that the value of I1 is equal to V1 divided by 8. Hopefully that's clear. And then the value of I2 is V2 over 3. And the value of I3 is V3 over 6. And now, there's some, let me just go through the steps here. it's a shame that, there's always many different ways of doing these problems. And so I want you guys to interact, but then when I show, and this is why the board will be much better, because on the board, I would be able to follow along in the order that you guys, that you guys are suggesting. Okay, so V1 over 8, right? That's I1 is equal to V2 over 3 plus V3 over 6. So that's just plugging in these three equations into this fundamental KCL equation. We also have that V2 and V3 are in parallel, right? So notice that V2 and V3 have the same connections on the top and at the bottom. And so they are guaranteed to be equal, which is very nice because we effectively have eliminated one of the variables. And so when we substitute that in, when we substitute this equation into here, we have that V1 is equal to 4V2. And again, the way I got this equation is by substituting in V2 for V3 in this equation. And then now we get to your suggestion, which was KVL along the left loop, which is -30 plus V1 plus V2 is equal to 0. In other words, the sum of V1 and V2 have to equal to 30. Okay, and we also know that V1 is equal to 4V2, right, from here. So we can substitute in 4V2 into V1 here. And so we have that 5V2 is equal to 30, or V2 is equal to 6. And
I'm
since,
sorry. I just have another question about
sure, go ahead.
the math that you did.
Yeah.
When you set V2 equal to V3, basically what I did was that instead of putting plus V3 over 6, I just put another V2 over 3. And that turned it into 2/3 V2. V1 over 8 equals 2/3 V2.
But the resistance 6 still has to hold. So you can put in V2 for V3 here, but you have to keep the 6 ohms.
Okay.
Right? Because that 6 ohms is not going to go away.
Okay.
But other than that, what you did is correct.
Okay. Right. Thank you.
So basically, the solution is to write KVL the way that you guys have suggested, and then substitute in these values here from above, which we got by applying Ohm's law. So each of these voltages here, V1, V2, and V3, can be written in terms of currents by using Ohm's law. And then what we get is V2 is equal to V3 is equal to 6 volts. And V1 then has to equal to 24 volts, right? Because we have that V1 is equal to 4V2. So now we have all the voltages, and to get the currents, we simply we use Ohm's law at each of these. So for example, to get I1, we divide V1, which is 24, divided by the resistance 8 to get I1 is equal to 3 amps. And similarly, I2 is equal to 6 amps divided by 3 ohms, which is 2 amps. And I3 is equal to 6 volts divided by 6 amps, which is equal to 1 amp. Okay, so are there any other questions on any of today's lecture?
Professor,
You're
I
on.
have a question.
Go ahead.
Can you hear me?
I hear you, but it's the sound is very distorted. Okay, maybe what I'll do is Yeah, I heard you a second ago. Yeah, go ahead. Type your question. This is scintillating video here. The suspense. Okay. Yeah, I understand. So let me back out. What I'll do is go back to that slide. The logic. Okay. So let me just, so V1 over 8 is equal to I1. Do you understand that? This is just if you apply Ohm's law, this resistor, you get that. Okay. Do you understand that V2 over 3 is equal to I2? Good. And then V3 over 6 is equal to I3. And so we then apply KCL at node A up here. So we have I1 splits off into I2 plus I3. And then we simply, we write those, we substitute in the Ohm's law equations, which are on the second row here, into the first row KCL. And we get V1 over 8 is equal to V2 over 3 plus V3 over 6. And so the step that I think you're confused on is that we can also equate V2 to V3. So V2 and V3 are guaranteed to be equal to equal because they're in parallel, right? So V2 and V3 have the same connections, and therefore they are guaranteed to be equal. And so then I simply substitute V2 for V3 over here. So we have, and now I'll try to annotate it just with text. So we have V1 over 8 is equal to V2 over 3 plus V2 over 6. So that becomes whatever the lowest common denominator. So that, that can be reduced to, let's see, V2, so a third plus a sixth is equal to a half. Yeah, the reason we know it is because they're in parallel. Because this node is the same as this node, and that both the top node of V2 and V3 and the bottom nodes of V2 and V3 have the same connection. Yeah, no worries. Right, so we have that. And so we have that V1 is equal to 4 V2. Okay, great. We've made it through the first week. We've made good progress. I wish all of you guys a nice weekend, and we will be back here on Monday.